Okay, anyway, so last time I just want to remind you that the point of scattering off a barrier is resonances. So what we did before was just we had a delta function. I can't think of a simpler barrier than a delta function. So delta function of x at 0 is, infinity at 0, but 0 everywhere else. And remember that you don't see any type of resonance behavior. But when we had double delta function, you started seeing behavior. I have to think about this. You started seeing this kind of behavior. And another one, the next one looks like this. So you see I have to draw the thing first. So this is 0, this is A, and then what you see, I'll do percent transmission, because I remember that a little bit easier. Percent reflection, percent transmission is on this guy. Percent transmission starts out kind of close to 0. All of a sudden it spikes, but then it goes down and up and down again. Of course, the maximum is 1. And the reason is because of the wave function basically adopts a particle in a box in between the traps, and I think I mentioned before, or maybe I flubbed that. One reason that this kind of makes sense to see particle in a box like wave functions in between is that particle in boxes have nodes at the endpoints. That's entirely why they work the way they do. And if the wave function has a node at the traps, then there is no trap, right? Because if the wave function is 0, the particle is never there. If it's never there and there's the trap, it doesn't know there's a trap there. So it just flies right through. Anyway, I don't think I explained that right the last time. And then we see these resonances. Once you have a double trap. So that's another thing. To observe the more interesting aspects of quantum this or that, you have to have some kind of complexity to the problem. Simple problems like this have kind of simple results. And that's great for you to build up and do a little math exercise, but you start getting into a little bit more realistic things, you see interesting phenomena. Last bit is this deal here. And as I mentioned to you, the finite barrier problem, I have the solution worked out on the website, and I do it by a brute force approach again, the name of the game here is the wave functions are, we start with the Schrodinger equation, which is a second order differential. The wave functions are known to us. They're e to the ikx and e to the minus ikx, and linear combinations are acceptable. So all you have to do is you have to get these coefficients. Now, where this is difficult is that the coefficients for the middle part, for region 2, have different k's. So that was a simplification to the delta function. You didn't have to worry about that. That ends up being just it just makes it a little bit harder. Now, of course, we assume that if the wave comes in and hits the barrier and gets through the barrier, that it only transmits. And that's just part of phenomenology. I don't know how to say that. And so we just have a right-moving wave. And note that the k's are the same. K1, K1 on the left and right. That's because the potential is summarily 0. So the amplitude will be less. I mean, some of the A wave, which we assume A is 1, assume A is 1, the amplitude will decrease because of the barrier. I mean, no way that's not going to happen. So the amplitude will be less, but the wavelength will be the same. So now the way you would do this again is you would have you'd have two equations, smooth and continuous, smooth and continuous. Now these were a little different. That's why they're kind of interesting. The wave functions are not they're continuous but not smooth, and so they're the trick. Remember, there's always a trick, and that's what I hate about this stuff. There's always a trick. The trick was to work with the Schrodinger equation itself. Here we're back to smooth and continuous. So you end up with two equations, smooth and continuous at 0, smooth and continuous at A, And now you have two equations. You seem to have 5 unknowns. A, B, C, D, E is 5. But if you just make A 1, then you've got 4 unknowns, B, C, D, E. And so, yeah, that's really all there is to it. One other thing to note that I glossed over this, but one of you sent me an email was asking about this. Percent reflection is actually, it's really the B coefficient over the A coefficient. The amplitude of the reflected wave divided by the incoming wave. The reason I said set A equals to 1 is what you do when you solve the system of equations. You actually solve it for B over A. That's how it actually goes. But it turns out that I've given you a shortcut when I did this. It turns out that you take all those equations, divide them all by A, and it turns out to be no different than just setting A equals to 1. It's mathematically equivalent, and this is just a hell of a lot easier to start out that way. The next thing I just want to say about this, because I'm not actually going to do this, is that I showed you some stuff on the computer. Oh, I was going to email you. I'm going to email you that code. God, sorry, I forgot about that. I'm going to email you that code that I used to solve this one. And maybe if you feel like it, you could apply it to this one. Save you the 5 pages. Again, if you look at the website where you see where I actually did this problem, and I did it by brute force. I solved for B, C, D, and E by using the linear, the system of equations. It was hideous. And I even solved for E squared, which is the percent transmission. And of course, you have to do this for E less than D and E greater than D. And what you get is a sinh K2A over E, whatever the potential barrier is, I call it B naught. 1 minus E over B naught. Okay, it's not very symmetrical. Sorry. So you can see that this is hideous, and I'm going to make it more hideous. I mean, this is awful. Oh my God! But it is what it is. Remember, this is really the amplitude squared. Whatever. So again, I would encourage you maybe to try that MATLAB, and instead of doing it by brute force, have MATLAB solve it. MATLAB can handle this one using that system of linear equations, lim solve and whatnot. Okay, there's a few, other than, okay, there it is, and again, it's the solution to a linear system of equations. That's really all there is to say. One thing that you can do is, it's kind of instructive, gives you a little bit of insight. You set K2 to infinity. Now K2, now you should know that K2, hopefully this is a knee-jerk reaction at this point. I'm praying that you know this kind of stuff. Technically E minus V over H bar squared. And so if E is less than E, this is imaginary. So maybe I'm going to do this. Put an I outside because E minus V is negative. And then I can just switch that around. Okay, so if this goes to infinity, that means that the potential is really, really wide. Another way to kind of approximate that is to make the width of the barrier extremely long. So, in other words, you have like an infinitely high potential or a long trap. And that's because you always see K2 and A multiplied by each other. You always see them together. So you can say the potential goes to 0. So, sorry, I should say, sorry about this, I should have played a little bit. A times K2 goes to infinity, so the high potential or a long trap. So that's a bad situation, right? That's, oh my God, this isn't going to work. But the point of this is that, and I want you to know how I figured this out, by the way. It's a limiting form of a sinh, K2A. So sinh of infinity goes to 1/2. Once the argument of sinh gets very large, e to the K2A. Remember, it's like sinh is like e to the x plus e to the minus x, something like that. So one of the terms you can just ignore. Okay, if you get that, then you get to this. Sorry, again, not such great use of the board. you get to this expression, and it is kind of like, well, so what about this? I mean, so I'm just writing a limiting form of a very, very large barrier. The reason that this is important is that, this is K2A, is that it's not zero, right? So that's the point of this. If I have an infinitely high and an infinitely, oh, let's make it infinitely high and wide. Why not? It seems like the transmission should be zero. It technically would be, right, it's exponentially low, so it is low, but it's not zero. So even for a really high and wide barrier, things still happen. So reactions occur that shouldn't. That's kind of your chemical input there. One of the ways I know that this manifests itself is like steric, like so like say a methyl group is trapped in like an ice. This is where a lot of this was seen before. A methyl group is trapped in ice. It's like almost 0 degrees. Well, the damn thing is still moving, right? It should not be, absolutely should not be, but it still does. And anyway, that's just an example of that. Okay, now let's forget all this. If E is greater than V naught, then the transmission is you know, I'm always calling sine squared. Is that maybe that's sinh? Maybe that's sinh squared. So I'm bothered now. I have to double check that. Maybe I've messed up the equation. That had that sine squared, so now it bothers me. I want that other one to be sinh squared, so I'll have to check that out. You know, like I say, there's always some obvious symmetries to these, and if I don't see them, it makes me nervous. So if I have a sinh sine squared here, I'm expecting a sinh squared there, so I'll have to double check that. And again, you can see like on the bottom, I have 1 minus E minus V naught, and then I've got E minus V naught minus 1, so that makes me comfortable. Anyway, these things always work out there. I just want to point out that when you're doing like E less than V, E greater than V, the answers always look kind of the same, but it's usually like sine turns to cosine and whatnot. Anyway, I just see that happening practically. Okay, now let's plot what that looks like. Let's plot percent transmission. Now it turns out, now again, I told you this before, and let's just plot a this is what you'd expect. So what I'm plotting here is E over V naught. This is the classical result. Remember that that's code word for if you were doing Isaac Newton mechanics, you know, velocity times time is position and all that stuff. You expect the car to break through the barrier once it has enough energy, and that's either it does or it doesn't, right? So that's what this should look like. And of course, this is percent transmission. This is 100%. This is 0%. Okay. Now it turns out that it depends. The nature of the percent transmission, the curves look different depending on how high the barrier is. It also depends on what the mass of the particle is. Anyway, so when I draw these types of curves, and then by the way, the YouTube entry, Wikipedia, the Wikipedia entry is mine on this problem. Just says that's anyway. Someone wrote something, but it was jacked up, so I fixed it. So it turns out that for some like kind of a higher barrier, you see this behavior. I mean, almost identical to what you saw yesterday with the double delta well. Again, the particle can transmit even when it shouldn't, so cool. And you see resonances. The thing that, so this is a high V. This is for a relatively high potential. Remember, high potential is relative. It's only relative for an electron, yada, yada, yada. And this is for a low potential. So that was really surprising to me when I saw these equations. I was plotting them, and again for an electron and a certain number of EVs of energy and whatnot. For a low potential, I got a curve like this. Here, 0, 0, right? that for a low potential energy, the thing can slip through even if it doesn't have enough energy. If it had any energy at all, it just slips right through. So anyway, I thought that was kind of cool, and you don't see that too often. The last bit is I want to point out that where you see, as we talked about last time, you're seeing the same thing again. So the percent transmission, if you look at that formula, the percent transmission goes to 100%, where sine was a K2A, right? K2A, where sine K2A goes to 0. And remember, that's because that's because you actually take the inverse of that expression. Okay, and of course we know that sine K2A will go to 0 when K2A is n pi. Okay, if K2A is n pi, I didn't want to put this on the computer. We did enough last time. This is a little bit more complicated to write out, to solve those systems of equations and to draw the wave functions. I just thought, you can kind of get it from what I did last time. But you end up with the same behavior. You're going to see a wave like this. Maybe it has more amplitude on the left side. And then you see another one like this. So again, you see particle in a box states. So on and on and on. So for when you solve the wave function for K2A is n pi, of course K2 gives you the energy for a given potential. Plot the wave functions, again you will see particle in box type resonances. The reason that this is important is, again, so many of us are doing research in argon and with X-rays. This is just an example, it's just kind of relevant because we're so close to argon and so many of us work in argon. It turns out that an X-ray with just the right energy will just shoot through an atom. Pretend it's not there. The reason that's important is it's kind of cool, like when you're doing absorptions, which is the log or log 10, I never remember, I over I naught, right? So that's our definition of what an absorption is. The way it works at argon is you have X-rays. You have an X-ray coming in, and your I naught is a box. It looks like this. I'm trying to remember what it looked like. It was like this. And there is a B and C cable here and here that goes to voltage. Okay, so what's happening is when X-rays come through, and then they traverse, and here's your experiment. And then there's another detector for the intensity. So this is the incoming intensity, and then another one of these is the outgoing intensity. And so the absorption of whatever your sample or experiment is attenuates, right? So I is less than I naught. All right, what's in here are gases, just rare gas. And when the X-rays hit them, they ionize. And if they ionize, they're going to head towards one of the charge plates. So basically what happens is that there's a burst of current that goes through it because the atoms are ionized. But if the X-rays are just right, you don't get anything. Because they'll just shoot through the atom just in the same way that they shoot through this barrier. Anyway, so that's an example. Another one that this one's kind of important. So you don't have to worry too much about that. But this one's kind of important. Nuclear decay. And I think in my first email I said, oh, this is the quantum mechanics of nuclear fission. It's because I had just written my notes on this. It turns out that people didn't understand, like when they were making anyway, when people were making isotopes, and you do that with nuclear reactors and whatnot, or atom smashers. The material, the heavier nucleus, too many neutrons, right, would not live, they live for a millisecond or so, and some are more stable than others. Well, why, right? They really didn't have any explanation until someone applied a tunneling, phenomenon, phenomenological model to decay, specifically beta particles, and alpha particles. An alpha particle is an He2+, and that's just a fancy way of saying 2 neutrons and 2 protons. Okay, so what happens is, so I'll draw that like this. It's traditionally drawn this way. 2 neutrons, 2 protons, no electrons, right? That's the whole point, no electrons. Okay, so here's the nucleus. And it's in a potential trap, and that's the strong nuclear force doing that. If you calculate, so the nucleus has a bunch of protons in it. Protons are right next to each other, and if you apply Coulomb's law, you get a force that would rip the planet apart just from a single atom. And so this is nuts. The atoms, the planet seems okay. So obviously there's a force counteracting Coulomb's force, and that's also what neutrons do. They're exchanging gluons or mesons or something. They have a strong nuclear force that keeps them together, and so that's what this trap is. But now, if this damn thing is going to pop out of the nucleus, what happens is that this is how it's modeled. You've got a trap due to the strong nuclear force, but if you get outside of that range, the strong force is considered to be very, very short range, then you've got technically a repulsive. I know this can be really confusing sometimes. I have to stare at this every time I look at this. The potential surface is repulsive. The reason is that since this is charged and the nucleus are charged, they're both positive. If it gets out of the nuclear, strong nuclear force regime, then it's going to be on a massively repulsive curve. And so anyway, the point being is that here's the length of your trap. There's your A in our problem. So anyway, it turns out that this would be, say, a low energy alpha particle. Let's say that the nature of the nucleus is such that the potential surface is more like this. This would be a higher energy alpha particle, and that's by virtue of the energy difference between that when it's far away, which would be like an alpha particle way out here would technically have no kinetic energy. So the way they do this, they can look at the kinetic energy of the particles. So if the nature of the nucleus is such that the alpha particle has a lot of energy, it has no energy, then you can relate that to the width of the barrier. Now, if you don't have a wide barrier, you're going to get out quickly, and you're going to do that at a faster rate. And there's a characteristic relationship between the energy of the alpha particles and how fast that the nucleus decays. No one understood why. I mean, it kind of feels right. Like higher energy alpha particles, the nucleus decays faster. It feels right, but why? I mean, well, that just makes sense. Well, why, right? Give me an equation. Well, this tunneling phenomenon, this model, gives you an equation. And it goes like the square root, like the rate of nuclear decay is like related to the square root of the energy, and that you can figure out by applying this phenomenology to that problem. So anyway, that's where the stuff comes into play. That's kind of important. But anyway, I'm kind of babbling on this. This is just kind of wrapping up our discussion of barriers and resonances. Now, for the most part, I want to get into grad school concepts. We can still kind of mired in what I think is still a little bit on the lower level, if not just complicated in an algebraic way. It's still kind of intellectually advanced undergrad level. So we're going to jump into a grad level concept, which is when the potential energy surface. I'm going to still do a potential energy in X. We're not worried about Y and Z yet. On next Monday, we're going to start doing multi-dimensional. Flat potentials, but multi-dimensions. And I'm going to do the particle in a sphere problem. Not a particle in a three-dimensional box. That's stupid easy. Particle in a sphere. So the potential surface will be flat, but it'll be multi-dimensional. What I want to do today is start talking about, I still want to do just a potential in X, one-dimensional, but I want to start talking about what happens when the potential surface is not flat, right? So that's real quantum mechanics. Okay, this is called the WKB approximation. Okay, and that's Winslow, Kramer, Bruin, and Jeffries. WKBJ sometimes. And Bruin was the guy who basically was the first person to do solid-state electronic structure theory. Kramer actually did a lot of reaction dynamics and solution. That's how I know him from a long time ago. So this is going to give us an introduction to how to think about what happens when there's some structure to the potential surface. It's called this is called a semi-classical. Semi-classical approximation, and by that we mean that h bar will be going to 0. So when I solve the Schrodinger equation and I shave off, so I'm gonna write the Schrodinger equation, I'm gonna expand it out as like a Taylor series, and then I'm going to make certain terms 0, and that's what that means. And so that's going to be my basis for making certain terms go away. And when those terms go away, then I'm left with something that's easier to solve. And that easier to solve thing, what that does is, it says that we still have wave functions that are like e to the ikx waves, but the k changes based on the curvature. So if the potential energy surface wants to go high, then the k is low. If the potential energy surface goes low, then the k is high. So anyway, so this is what happens when your potential surface is no longer just flat. Remember, steps don't technically count. So again, the whole idea of this is, again, there's two things. Semi-classical, and that means h bar goes to 0, and you'll see when I do that. And the ultimate idea is to get you to understand what happens with wave functions. It's a way to think about wave functions, and wave functions are particles. You shouldn't think of particles as particles. You should think of them as waves. So an alpha particle, it's a wave, right? Your chemicals, they're waves. The wavelength of the particle gets long at a high potential area, and it gets short in a low potential area, and this is a way to show that. So, and physicists are kind of obsessed with this. Okay. So again, for V of x not flat. What I'm going to show you, though, is that this approximation is perfect for when the potential is flat, and that just means that I'm comfortable with it. That's all that means. Okay, so what I want to do here is, let's start out with this thing, and again, I will make it easy by not going past x, because that's all we need to do. What we're going to apply this to, we're going to apply it to a harmonic oscillator, because harmonic oscillators are like very important, obviously, to describe bonds. What's also important about them is that they're in one dimension. You can think of the distance between the two atoms as just being the x dimension, which is kind of awesome. Okay, now I'm going to do one simplification. I don't want you, I tend to, one reason I think I'm going too slow is I want you to see every step. Because I know sometimes if a step suddenly comes out of nowhere and you're like, well, what the heck, now I'm lost. Even if the remaining steps are rather simple, you're lost. It doesn't matter if the remaining steps are simple or not, you're lost. So anyway, so I tend to do every step. So Schrodinger equation, like we learned it in undergrad, so I just brought the E over, nothing to that. So if V is constant, remember that we have these wave functions. Remember that K is square root of 2m E minus V over h bar squared. That may or may not be imaginary. Again, we've done all that, so, okay. So, the WKB approximation, let's say that the wave function is going to look like this. E to the I over h bar S of x. Now that's an S, that's not an integral sign. Let me make that I better. There we go, that's a nice I. Okay, that's S of x. It's not an integral of parenthesis of x. That's nonsense. This is a function, S of x. Again, the point is that if the potential is high, so this is like our K, right? There's an x in there somewhere. So this is going to get high, which is short wavelength, if you have a lot of energy, and you have a lot of energy if there's low potential, and vice versa. So that's the idea. And again, it still preserves the very wave-like nature of a wave function. So there you go. Let's see what I want to say about this. Okay, the next thing is S of x has h in it. Okay, now I know that because a wave function, e to the argument of an exponential cannot have units. That's not allowed. It doesn't, remember that exponential functions, you can put them as Taylor series, 1 plus x squared. If x has units, you're getting nonsense. 1 has no units. X has units of 1 over h bar. H bar has units of joule energies. Joule time, joule seconds, sorry about that. Anyway, you can't have an expression that's no units plus units squared plus units cubed. That just is absolute nonsense. So that means that this function, S of x, has to have an h bar in it to cancel out the h bar here. Now the reason I'm saying this is because, it's like, well, okay, well, so what? So often in math, I'm like, multiply and divide by 1. Why? Well, because that gives you the answer, right? And of course, it's always clever. When I say multiply and divide by the same number, it's always clever how it comes out. Okay, so S of x is going to be expanded as a series. Now, this is something that always kind of bothers me. We're going to expand it in a Taylor series, but not in x like you expect. X is your dependent axis, right? Sorry, your independent axis. I'm not going to do that. I'm going to expand it in h bar. I'm guessing you've never seen that before. I still find this weird. I'm going to expand it in units in terms of a constant. But it turns out you can expand anything and anything. I know you're used to Taylor series, but you can also do things like this. This is called the Lorentz series. The Lorentz series, which is one of the most important mathematical entities that exists. And I'll explain. I hope to cover Lorentz series one day. And the way it looks is you have a function, and you're going to expand it in powers of x. So it sounds like a Taylor series. Like if I start at x0, x to the 0, it's starting to look like a Taylor series. Right, so this looks like a Taylor series. What you don't expect is that you also go backward, right? Forward in x, x to the 0, x to the 1, x squared like a Taylor series, but you also can go backward, x to the -1, x to the -2. So anyway, so you can expand anything as a series, and there's more series than you've ever heard. And you can imagine that if x has units, then these a's have units too. So that's kind of my point. So imagine that if this x has units of h bar, then this is h bar squared. That means a to the -2 has units of h bar squared. If that's h bar, then that has h bar. If this has units of h bar, then a1 has units of inverse h bar squared. So anyway, just calibrating you towards that. And I also wanted you to see a Lorentz series because they're kind of horribly important. Okay, with that said, and if you're okay with doing something really kind of weird, which again is expanding things as a series of constants, and that's kind of my example up there. What I'm trying to do is point out that as much as that Lorentz series is an expansion in x, a little unusual than what you've seen before, still it's an expansion of x. I could say it's an expansion in a too, right? I could say that. I mean, it's relative. These are just letters anyway. I could say that it's an expansion in these coefficients, where this one has units of h bar squared, and this one has units of -h bar squared, and everyone in between. That's perfectly acceptable to say that. And then to say that I have to figure out what goes on bottom. And it happens to be x squared, and this term happens to be 1 over x and whatnot. So that's just another way to look at that. And so that's why I'm saying I'm going to do this. Take that function s of x, let's have it as S0, which has, let's say that this has H bar units. Then we're going to multiply this, which of course would have no units. So remember that if you look up here, I've got 1 over H bar. So this guy has H bar, that's good, so you end up with no units at all. And then again, the whole point was to expand in increasing powers of H bar. And then this has 1 over H bar units. Sorry, I shouldn't be, I'm not writing this part right. The function has 1 over H bar units. Sorry, I stupidly included that. That's not what I said. So remember, I know this seems off, like, no, wait, this has H bar units, but you're dividing out an H bar right there. So that's why I'm saying this. So just don't get confused. When you read your, I know it's like stupid obvious now, but when you read your notes, you're going to get confused. Okay, so what we do is plug this into this, and what do you get? The first step is minus H bar squared over 2m. Now let's do the first derivative. Again, I'm gonna do this in baby steps. And now you have to do the derivative of e to the function, e to a function. And the solution is the derivative of that, it's the derivative of the argument. And so I'm just going to call that the derivative. And then of course exponentials always survive. They always survive differentiation. And again, I know my s's look like integral signs, so just be careful of that, because I've got those with integrals everywhere here. Okay, now what's this equal to? Now we've got ourselves a product rule, so this is kind of a Bismarcker. So I'm going to take that minus H bar squared over 2m. I'm going to factor that because I've got a bunch of terms now. I've got I over H bar. So what we can do is do the derivative of the first term. So which is the derivative, so now it's a double derivative. Now, I've got I over H bar. I'm going to leave that derivative alone. I'm going to do that again. Okay, well, that brings down another I over H bar. It brings down another derivative of the function s of x. So that's now squared. And sorry, this bracket needs to be bigger, or it's not perfectly symmetric. There we go. And then, of course, all this is multiplied by e to the I over H bar plus of x. So I just factored that out. And, of course, on the other side, we have e minus. So I just move that on over. Again, I hope you're not, I've done actually a couple of steps of algebra, and I just contradicted what I said earlier. When you do that, I just did. So again, I did the first term, I did the double derivative, just product rule, just got to be a little careful with that. On the other side, I just brought the v to the other side. Why did I do that? I went the wrong way, sorry about that. Anyway, so that's over there, and the point is, you can see the point of this now is that those terms divide out. Okay. So, what you're left with is, now I'm just going to simplify this. What I'm going to do is I'm going to bring the H bar squared over 2m to the other side. Oh God, what am I going to do here actually? Let me double check what am I doing. I feel like I've got myself a little, tell you what. Yeah, let me simplify this a little bit. I've got minus H bar squared over 2m times minus 1 over H bar squared S prime of x squared, right? So that ends up being plus 1 over 2m. Okay, now I've got minus h bar squared over 2m over times I over h bar s double prime of x equal to still e minus v of x, e minus v of x. Right. Okay, next step. By the way, your textbook has a section on this, but it's really incomprehensible. You're going to want to, if you just Google this, you can find plenty of pretty good set of notes on how to do this, and that's basically what I did. And then I filled in some of the in-between steps to make it a little bit easier. Okay, so now I'm going to simplify it further. What I've now got is s prime of x squared. Notice I'm not being very consistent with my brackets. What I'm doing is I'm multiplying everything by 2m. So the first term is 1 over 2m derivative squared, so I'm going to multiply everything by 2m. So what have I got here? I've got a minus I h bar. I know it's over 2m, but I'm deleting that. Double derivative of x is equal to 2m e minus v of x. And this we are going to call p of x squared. Okay, so I want to point out is that if this is energy minus potential, then that's kinetic energy. So what I've got here is 2m e minus v is p squared over 2m. 2m times p squared over 2m, so that's p squared. So it's momentum squared. And often we just do this so that we don't have to write all this out. If I can just write that instead of that, it's easier. So that's one reason you do that. Okay, last bit, I'm almost done, so this is where we're going to start making approximations. There's actually nothing wrong with this. But let's say that if S is slow, okay, so S of x is slowly varying. So now remember S of x's job. It represents the momentum, it's the K, it's our new K, kind of. It's going to be short wavelength at high energy and long wavelength at low energy. But if the potential surface is not too curvy, we don't expect it to change much. It's not like some crazy, it's not crazy funky, it's rather bland. If it's bland, then the derivative probably isn't strong. It's probably close to 0. The double derivative would be a very small value. So therefore, you'd say that the second derivative goes to 0. Okay. So if that's the case, then what you've got is this. You've got the derivative squared minus I h bar goes to 0 equal to p of x squared. Okay. So, in which case now you've got yourself a really simple equation to solve. You've got yourself, you see the point of this is that, and I'm actually going to largely stop here, a derivative squared equals to a function. In terms of solving differential equations, this does not scare me. Of all the things I can see, I'm just going to take the square root of this and then just bring dx over and integrate it. Anyway, it looks really easy. It looks insanely easy. Okay, I want to point out if v of x is a constant, then what you end up with is, I'll write out the derivative now. So I'm just making that little dash what it really is. If this is true, then px squared is actually h bar squared k squared. And k is, of course, square root of 2m e minus v over h bar squared. Okay, so remember, for waves, h bar squared, h bar k is the momentum, so the square is h bar squared k squared. So if you end up with this, and then I can tell you that in that case, S is just the integral of plus or minus h bar k dx, which is plus or minus h bar kx. And the wave function, sorry, I just realized what time it is. E to the plus or minus ikx, right? H bars cancel, and then I'm just looking at ikx. Okay, anyway, so again, we're making this approximation. There's really no approximation here. This is actually fine. Here we're starting to do things, and I'm just showing you if the potential is flat, then we actually get the perfect answer. Everything is completely fine. So next time, I'm actually going to let the potential will actually be some kind of function, and we'll go from there. Sorry, you got to go. Okay, so that's that. Yeah. I talked too much at the beginning. So anyway, so this is just half of the derivation. I knew I wouldn't finish. I planned to get this far today. So the next time you'll see the complete derivation, and then we'll get wave functions, and then I'll also share how to calculate energy. So remember, and also in the big picture of flow, the flow of things work. You have a differential equation. You solve it. By solving it, I mean you get wave functions. You then plug the wave functions back in, and you get energy. So we're slowly solving wave functions. Again, I solved the wave function in a simple case. We'll solve it in a more complex case, and then we're going to use that to get energies. And then you have a homework problem on this, which is you might want to start looking at the problem. Heads up. All right. So with that.